Hi J1s, even J2s. Now you might have some problems with balancing of redox equation as of now and solving the unknown oxidation state. Hopefully this short video will be able to help you conquer the two concepts, right? Now let us start now. Now I personally prefer the oxidation number method. Now this is the reason why. Now in redox equation is all about transfer of electrons between the two crown atoms, and the electrons transferred basically controls the mole ratio between the two crown atoms. Now if we basically can work out the 2 mole ratio, the crown atoms mole ratio right at the start of the first step, that will make us get the mole ratio as soon as possible. Now why am I talking about mole ratio that many times? It is because most of the questions that you are looking at, okay, basically they are asking you more on to solve stoichiometrically the amount of certain species that reacts in a redox reaction. They are not that concerned with balancing of equation, not all the time, okay, maybe sometimes, but not all the time. Now, so therefore, how do you, as fast as possible, get your balanced equation, get your mole ratio, so that you can solve the question? And that is your answer. Use the oxidation state method, okay? Now, in the oxidation state method, we focus in getting the mole ratio in the first step. Now, you might be taught in school that you will be adding your electrons in the last step. So once you get your electrons added in the half equation in the last step, then you get the mole ratio, then you get the full balance equation. By that time, maybe a good 5 minutes is gone, all right? So if your question only focuses on getting the mole ratio, you should consider this method, and it's really, really very fast. You just need some practice, all right? So now, first of all, whenever you want to balance a redox equation, you always have to make sure the crown atoms are balanced, okay? The crown atoms are the atoms that went through the reduction and the oxidation. The crown atoms are the atoms that went through oxidation number increase or decrease, okay? So these are the crown atoms. Now these atoms must be balanced first before you work out balancing of the electrons in. So what we do is we balance the crown atom, we count the oxidation number state for the reactants and the product, calculate the change. This oxidation number change will be equal to the electrons that is required for crown atom to be reduced or oxidized, okay? So you need to add in your electrons to get, therefore, later on the mole ratio, right? I'll show you a demo, then I will work with, I will practice with you the fast method, right? So after doing step number 1, you get a mole ratio. Now let's ignore step 2 and step 3 first, because really it is step number 1 that gets you your mole ratio, and in any balance equation, once you get the mole ratio, you can solve the question for calculation, all right? Now, so for example, what you have learned in school thus far, it is first to work with half equation, and in each of the half equation, now I am using the oxidation number method, meaning we count the oxidation number, right? And we count the oxidation number of manganese. So manganese now is the one that goes through the reduction. So from +7 to a +2, okay? Now, so from +7 to +2, it is a decrease in 5 units of oxidation number, meaning it has gained 5 electrons, okay? MnO4 minus, your permanganate, has gained 5 electrons to become your Mn2+. Now, how about iron 2+? Iron 2+ is the redox partner for MnO4 minus. So iron 2+ from +2 to become +3. So this is a good 1 oxidation number change. Okay, so this is a 5, and that is 1. Now, if there's 1 oxidation number change per iron atom, therefore it means that it must have lost 1 unit of electrons. Now, just take note, your reduction electrons should always be on the left. It gains electron, and for oxidation, your electrons should always be on the right. So once you calculate the units change, the number of electrons will be reflected by the number of units change, but you need to make sure that electrons are on the left for reduction, electrons are on the right for oxidation. Now, so how do we get mole ratio? Basically, okay, remember the key thing. electrons is the one that controls the mole ratio between the redox species, because redox reaction is all about electrons transfer, and in the electron transfer it leads to oxidation number increase or decrease for the crown atom. All right, so therefore, to make sure that the electron transfer are exactly equal for the reduced and the oxidized species, you need to multiply by 5, okay, for the half equation for iron 2 plus to iron 3 plus. Now in that way you get iron, okay, 5 of the iron 2 plus to form 5 of the iron 3 plus, and releasing 5 moles of electrons. Electrons must be all cancelled on the left and the right when you basically combine the two half equation. So here you have your mole ratio. You have 1 unit of MnO4 minus proportional to 5 electron, which is proportional to 5 units of iron 2 plus, and you can go ahead and calculate your stoichiometry. So you see, you don't have to have a full balance equation. Okay, now this is what you should learn from school. Let me teach you a faster method. Okay, now so let me teach you a faster method. So let's go to, let's say, this equation number 1. Okay, so I'm just going to balance it directly on the screen itself. If you need to copy down, please take some time to copy down. You can always pause the video, but I'm going to start straight away. Now, so there are 2 redox species here. The crown atom is chromium, right, highlighted in blue, and iron 2 plus highlighted green. All right, so let's solve for iron 2 plus and 3 plus. Now I'm going to balance not half equation but a full equation together, right, in one shot. That will save a lot of time. So what you need to do is to basically sync the similar crown atoms and count the oxidation number change. So this is from +2 to a +3. All right, so therefore there's 1 unit of oxidation number increase. You use 1 electron per iron. So I'm going to write 1 electron here. Now how about chromium? Chromium is a little bit harder because why? The crown atom here, there is 2, there is only 1 here. Okay, so what you need to do is to multiply by a 2 for the right hand side, for the CR to be 2 CR3 plus, right? Then you count the oxidation number. So this is a +6 and that is a +3. So there is 3 units of electron change per crown atom. So there are total of 2 crown atoms, and therefore it works out to be using a total of 6 electrons. Now, so therefore, what is the mole ratio? It is to make sure that the electrons for the reduced and the oxidized species both balance each other. So in order to do that, you multiply by 6 in front of your iron 2 plus to iron 3 plus, and there you have your mole ratio is out. You have 6 iron 2 plus reacting with 1 dichromate. Okay, so isn't it very fast to get a mole ratio? Now, if you are interested in getting a full balance equation, what you need to do next, okay, let me look back at the screen first. What you need to do next is then to count the overall charge on the left and the right. You add H plus if it's acidic medium, you add OH minus if it's alkaline medium. So the benefit of this, okay, method is you do not add H plus first and then later on use OH minus to neutralize the charge. That takes too much time also, right? So basically just count the overall charge. If you are having the redox equation in the alkaline medium, you're adding negative charges. If you are doing the redox equation in the acidic medium, you're adding positive charges, okay? And then after you calculate your charges, you balance the O, you count the number of O's on the left and the right, and add equivalent number of water, okay? So let's get back to this part again. So after the first step where you balance the electrons, what you need to do is to count the overall charges. I'm just going to erase the oxidation number state first so that you can see the charges properly. So let me erase the oxidation number state. Now the charges is really what you see as the overall charge. So on the left hand side, we have a -2 on the dichromate and a 2 plus, but please remember you have a 6 there, okay? So you need to get 6 times 2 plus, so you have a 12 positive charges minus a 2 negative charges, you get a 10 positive charges on the left hand side. And on the right hand side, you have 2 times 3 plus, it is a total of 6 positive charges, plus 18 positive charges, you get a 24 positive charges. Now, if I have to balance this in an acidic medium, I have to add positive charges and make sure both sides has the same number of positive charges, okay? So since there is a 24 there, you should be adding another 14 positive charges of H plus, such that the charges on both sides of the equation is balanced, right? So therefore, what you need to do is to add a 14H plus here, all right? Now, then you should be counting the oxygen. So there's a 7 oxygen here. So let me write down 7 oxygen atom on the left and 0 on the right. Okay, so therefore, in order to balance the oxygen atom, you should be using water, okay, to provide the oxygen. So basically, as the last step to check your number of hydrogen, on the both sides of the equation, it must be balanced. So 14 on the left, 14 on the right. So your balanced equation is definitely going to be correct, okay? So let me just use these and recap the steps for a while. Number 1, okay, balance your crown atom, right? Count the oxidation number, balance the electrons. So make sure when you balance the electrons, especially for atoms that have more than one crown atom, the way to calculate this is the number of your crown atoms, okay, multiply by the oxidation number change. That way you get the total number of electrons that is gained or lost for that particular half equation, right? So after that, then you'll have to make sure you count the charges, okay? And then using H plus or OH minus, which I'm showing you the next equation. And then you count your oxygen to balance with water. Now just bear in mind the 3 species therefore that we are always adding in balancing of equation is your electrons, H plus or OH minus, acidic alkaline medium, and water. Do not attempt to add any other species because, for example, many students always think that it's okay to add oxygen. If you are using oxygen, right, the problem is that oxygen to be water is in fact a reduction. So you do not want to introduce a unexpected reduction, right, while balancing a half equation for the intended crown atoms. Okay, so just take note of that. Only electrons, H plus or OH minus, and water, okay, to be used in balancing. Now, if we look at the next one, we start with H2O2. So H2O2, right, if you see properly, right, it should be the O2 that went through, the oxygen atom that went through the redox change. So let's count the oxidation number. Hydrogen, when it's bonded to non-metal, it should be a +1. So this oxygen is a -1, right? The oxygen in oxygen gas, okay, is a 0. So since there are 2 crown atoms, it will be a 2 times how many units change of oxidation number from -1 to 0, it should be a 1 unit change, okay? So therefore, from H2O2 peroxide to O2 is a 2 electrons transfer. Now the next one is your Cl, okay? So ClO2 here, it's a +4, right? And this ClO2 minus is a +3. Right, if you count the oxidation number, +4 to +3 is a transfer of 1 electron since there is only a chlorine atom, so you don't have to multiply by any factor, all right? Now, so therefore, from here, you can get the mole ratio. You have to multiply by 2, okay, in front of the ClO2 and the ClO2 minus, so that the total number of electrons transferred will be 2 electrons, and the mole ratio will be H2O2 proportional to 2 ClO2, okay, because they utilize a total of 2 electrons, right? Now, again, if you are interested to continue in balancing the equation, then the next step is to count the overall charges. Now, remember, do not take the oxidation number as the overall charges. Your eyes should be focusing on the charges, the real charges on of the ions, okay? So therefore, on the left-hand side, we have 0 charges. On the right-hand side, we have a -2. Okay, 2 negative charges. So 2 negative charges, right? Now, since it's basic, meaning we have to add OH minus. So in order to add OH minus and in order to balance the charges so that both sides becomes a -2, we have to add here, we have to add 2 moles of, okay, OH minus to the left-hand side. So there you go, adding 2 moles of OH minus on the left-hand side so that the charges is -2 on the both sides of the equation, okay? Last step, count the oxygen. So please count properly because each species here carries some oxygen atom. So you have 2 for the hydrogen peroxide, you have a 4 for the Cl from the 2 units of ClO2, and you have another 2 from the hydroxide. 8 oxygen atom on the left, 2 + 4, 6 + 2, 8. Then next one, you on the right hand side, you have 2 oxygen atom and you have another 4. Okay, so it's a total of 6 oxygen atom. And therefore, you have to add water on the right hand side. So therefore, on the right hand side, I have to top up with the 2 units of water to balance the 2 oxygen. So one last double check, your total number of hydrogen on the left should be 4, right? So 2 with the OH minus and 2 on the hydrogen peroxide. All right, so that's your balance equation. Now let's look at the next one. The next one is slightly interesting, and I'm sure your teacher have went through with you. Okay, when you have one species forming 2 separate products, this is your disproportionation. Okay, it comes from the word distinguish, means you have 2 different products, right? 2 different products for this redox equation, which means chlorine is both reduced and oxidized. So in this balancing, I would like to split chlorine up, one for the reduction and one for the oxidation. Okay, so let's begin. Now, I'm going to count the oxidation number. So both of the chlorine will start with a 0, and this will be a -1, this will be a +5. All right, so basically you just need to link each chlorine to one of them. So for example, chlorine to chloride. Now bear in mind, the crown atom, chlorine, must be balanced first. So make sure you multiply by a 2 first, okay, before you start, okay, adding the electrons. So what is the total number of units change, oxidation number change per chlorine is from a 0 to -1, so 1 unit change. But you have 2 chlorine atoms, so total of 1 electrons for 1 chlorine. Since there are 2 chlorine, you need a total of 2 electrons. Now the next one, chlorine to ClO3 minus your chlorate is from a 0 to +5. Now, if you don't take care, many students will write a 5 electrons here, which is wrong. Why? Because the crown atom is not balanced yet. So the Cl2 here must multiply by a 2 first. Then you can calculate the total number of electrons change. So each chlorine went through 5 electron unit change. That is definitely correct. However, there are a total of 2 chlorine atoms. Okay, so you kind of need a total of 10 electrons for this reaction, and therefore we need to multiply by 5 in front of this half equation connecting Cl2 to Cl minus. So 2 times 5, oops, I need to have a 10 Cl minus here. Okay, so therefore, again, your balance equation is out. Now I do need to add these 2 together. So 1 plus 5, it gives you 6 Cl2 is proportional to a total of 10 electrons, which is proportional to 10 Cl minus and 2 ClO3 minus. Okay, with this mole ratio, you can go ahead and calculate anything that the question asks for, right? Now, if you are interested to balance the full equation, then that's when we continue to count the charges first. On the left-hand side is a 0. On the right-hand side is 10 Cl minus, so 10 negative charges plus 2 negative charges here. So you have a total of 12 negative charges, right? So since we are balancing in a basic medium, we are adding negative charges to the left-hand side, so 12 negative charges. All right, so that both sides is a total of 12 negative on both sides of the equation. And the last step will be easy, just count the O. So on the left-hand side, you have 12 O, so this is 12 O. On the right-hand side, you have a total of 3 times 2, so 6 oxygen atom. And therefore, to balance, you need to add 6 units of water molecule here. And check the hydrogen, both sides should be a total of 12. Okay, and so that is your very fast redox balancing equation. I hope you can catch it, okay, because it's really important to do all this as quickly as possible. All right, now the next one that most students have, it is actually solving your unknown oxidation state. Now, in fact, is this a very challenging concept? Not at all, because why? Instead of walking forward, you are just walking backwards now. Why am I talking about that? Now, let's recall what we did just now. Now, in balancing your redox equation, what we did was first, okay, we calculate the oxidation number change per crown atom. Basically, then after that, once we calculate the oxidation number change, okay, we kind of get the total number of electron transferred, and from there we get the mole ratio, right? And from the mole ratio we can calculate the amount, right? Now how does your calculating of the unknown oxidation number work? It works backwards. So what the question will provide you is the amount of substance. Some questions are kinder, they provide you with the mole ratio directly. So if you start with the amount of substance, make sure you work the mole ratio first. Once you are given the mole ratio, you work out the total number of electrons transferred, okay? Now this needs, okay, what does this total number of electrons transferred need, okay? You need to have a half balance equation where it is a reduction equation or oxidation equation. Now this is coming from your known species, so it is from a species that you know, not the unknown, okay? Then from there, you are going to work out the electrons. Using the electrons, you are going to work out the oxidation number change per crown atom. And therefore, you kind of maybe need to calculate the original oxidation number change, either the original, you need either the original or the final, okay, to calculate, to solve your question. So it is really working backwards. So instead of balancing straight away, we are actually getting the mole ratio first, okay? Now, so let's start with the first question. If you need time to read the question, please feel free to pause the video. I'm just going to start to guide you along the way. Now, my recommendation is that you always identify the species, redox species, the species that's reacting with each other, right? So read the question, they will definitely give you information for that. So S2O3 2 minus reduces Cl2 to Cl minus. So in this sentence, it means that Cl2 is forming Cl minus, is reduced to Cl minus. S2O3, which is the partner of Cl2, is being oxidized to some unknown oxidation state, okay? So then what other information do they give you? 1 mole reduces 4 moles. So good enough. They give you 1 unit of thiosulfate reduces 4 units of Cl2, okay? Now this triple line, okay, like a sun in the Chinese character, it is not equal sign, it is equivalent sign. It is a ratio, okay? It's a ratio. So take it as a ratio. So every 1 unit of thiosulfate uses or required 4 units of Cl2. Now, so therefore, we get the mole ratio, we need to get the number of electrons transferred. Now, to get the total number of electrons, to insert the electrons into this mole ratio, I kind of need to look at my known species. Now, my known species is Cl2 to Cl minus, okay, because my unknown is sulfur, okay? What is the sulfur containing product in the final product that is formed, right? So what I need to do is to practice balancing of half equation, right? So if you are well practiced with the oxidation number change method, you will balance it very quickly. So from 0 to a -1, don't forget, balance your crown atom first, okay? So before you count the total number of electrons, please make sure you balance the crown atom. So the total number of electrons transferred, okay, for Cl2 to 2Cl minus, it is 2 Cl atom for every 1 electron, because every chlorine, okay, goes through a 1 oxidation number unit change. So 1 electron is involved. There are 2 chlorines, so 2 times 1, all right? So 2 electrons. Now, how do I write a balanced half equation for the reduction here? This is reduction, so make sure your electrons are added on the left. Okay, and there you go. You have a mole ratio already. So therefore, if 1 unit of Cl2 uses 2 electrons, 4 units of Cl2 uses a total of 8 electrons. Okay, now what is Cl for? It is like a middleman to bridge your thiosulfate S2O3 2 minus to your 8 electrons. Okay, so therefore what we understand is your S2O3 2 minus will basically lose all the electrons to form a certain product, right? Now, so let's look at this a little bit carefully. Now, in your, what we have now is the electrons. Now, we need to work the oxidation number change, okay, before we find the final oxidation number for sulfur in the product. So, the original oxidation number here is a +2, okay? You can go and count. Now, make sure you know that the product that is going to form, that sulfur is going to form, right, it must be a 2 sulfur unit, right, because there are 2 sulfur atoms. So, I'm just going to balance the crown atom, right? So therefore, if it's 8 electrons, it means that out of the 2 sulfur, each sulfur atom, okay, I'm going to write 2 sulfur here, each sulfur atom actually uses 4 electrons. So in total, they utilize a total of 8 electrons, okay? So therefore, this will represent the oxidation number change. So it will basically tell you what is the final oxidation state of the product here. So plus 2, you must oxidize. That means the oxidation number must increase by a good 4 units. Okay, so therefore plus 2 plus 4, you get a plus 6 in the product. So plus 6 in the product, your answer can only be a C, which is SO4 2 minus. Okay, now let's practice a few more times to get the hang of it. Last 2 questions. Vanadium 2 plus can be oxidized. So great, they tell me vanadium 2 plus can be oxidized already by Mn permanganate 7 ions. So you need to know this, okay? So these are the prerequisite, okay, that you need to know, the MnO4 minus in an acidified medium to form VO2M plus. So they told me the product, but M is unknown. So we have to solve for the M. So in the experiment, you have a certain volume and a concentration. You can calculate amount. Okay, so the amount will be, I'll let you do the calculation for yourself. This should be a 0.0005 mole. Then after that, your MnO4 minus of that certain volume and a concentration, you'll get your amount of MnO4 minus to be 0.0003 mole. Okay. Now, so then they say find M. That's all they give. So let's see how we can analyze from whatever data that is here. Number 1, since I have the amount of both species, I'm going to get mole ratio. So from the amount, we get mole ratio. So mole ratio of V2 plus to MnO4 minus is 5:3. Okay, so 5:3. All right. Next, I'm going to insert the electrons here. So how many electrons does this tally with? Now I need the half equation of the known species. The known species here is MnO4 minus. Now, however, they never tell you the product, which therefore that comes under the prerequisite of you need to know when it's acidified, your MnO4 minus forms Mn2 plus, okay, as a product. So with that, you need to balance first. Okay, not really balance, but get the oxidation number change. Okay, the total electron transfer for the reduction of MnO4 minus. So Mn here, crown atom is balanced, plus 7 to a plus 2. So per Mn, per manganese, is a 5 electron unit change. Okay, so let me put the 5 electron in the equation so that you can see the mole ratio a little bit clearly. So therefore, I don't have to balance the half equation. I just need this unbalanced, okay, half equation, because basically I just need the mole ratio between MnO4 minus and the electrons. So since there are 3 units of your MnO4 minus, 1 unit give 5 electrons, 3 units must give a total of 15 electrons, right? So that's what you need. Now this is the most crucial part. So what you need to do next is to basically find out how many units of vanadium 2 plus, okay, is proportional to how many units of electrons. So you have a total of 1:3, right? 1:3 also means that the oxidation number change must increase by 3 units, okay, because this is oxidation. Now, if we increase by 3 units from the plus 2, it must increase until a plus 5, right? So that will mean that M here is a plus 5 minus 4, because 2 times 2 units of the O2, and M is plus 5 minus 4, M is equals to 1. Okay, so that's how you solve this question here. Right, now let's try something really very difficult. Well, if you practice much, it won't be too. Now this is an A-level question, which our seniors, quite a lot of them have issues with this. So let's go through. Now, iodine is oxidized by nitric acid. Read the whole question first before you decide who is the redox species. So iodine oxidized by nitric acid. White crystalline solid oxide. So this is the iodine oxide, can be isolated. 0.001 mole of this oxide. So it's about the oxide. It's nothing about the iodine. It's nothing about the nitric acid. Okay. So 0.01 mole of this oxide reacts with 0.01 mole of iodide to give you 0.06 moles of iodine. Now what they are trying to say is basically iodide, I can hear, okay, I mean I can see, right? I minus, it is forming iodine. So what happens is the oxidation, because the oxidation state of iodine changes from -1 to a 0. Okay. Now therefore it means that the oxide, the iodine oxide, now let me write a representation for it. So let's say I represent by In plus, okay, because I don't know how many units of iodine is in this oxide and what is the oxidation state. So I'm just going to represent with the In plus. Okay. Now, so both of them react to give only iodine. So basically your iodine oxide, were represented by the In plus, is also forming iodine, right? So this is a reduction. Now what we call this is basically this is two different reactants, reduce and oxidize, to give you one similar product. This is what we call a combined proportionation. So instead of disproportionation, it's a comproportionation, right? Now, so what else? What other information did they give? Number one, they give 0.001 mole of this oxide. So I'm just going to represent with this. Okay, is proportional to 0.01 mole of I minus. Okay, potassium, all group 1, group 2, group 3 cation ions, you can kind of ignore. They don't go through redox very easily. Now, so this mole ratio, back to the mole ratio. The mole ratio here is 1 unit of In plus is proportional to 10 units of I minus. Okay. Now, bear in mind, we go back to the half balance equation, the reduce and oxidize half equation, to find out what is my unknown, what is my known. So the unknown is this, and the known species is your I minus, which means I need to balance the half equation between I minus and I2. Okay, so first step, make sure the crown atom is balanced. So there are 2 I minus. The oxidation number change total is 1 iodine went through a unit change of 1, because from -1 to 0, since there are 2 iodine, is a total of 2 electrons, right? 2 electrons. Now, so there we go. Okay, if I am going to put in the electrons in the half equation, it will be placed here because this is oxidation. Now all we need is this, because this is my redox species, 2I minus to 2 electron, meaning 10I minus to 10 electrons. Okay, so it means that the oxide, this oxide, uses a total of 10 electrons to form your iodine, right? To form your iodine. Now, therefore, let's work backwards, okay, a bit. So this is 1 crown atom, but this is 2 crown atom, right? So when we balance, we must make sure that the crown atoms must be balanced first. Now, so in fact, it means that there are 2 units of iodine atom, and they total up to use a total of 10 electrons. So how many electrons did 1 iodine atom use? This is fairly simple for you. It will be a total of 5 electrons. Okay, so 5 electrons will mean that your oxidation number, because this is reduction, must reduce 5 times. Must reduce your oxidation number of your iodine must reduce by 5 unit. Okay, so from something to a 0 per iodine, because each iodine only can use 5 electrons. There are a total of 2 iodine, so each iodine uses 5 electrons, 2 iodine uses 10 electrons. Now this iodine oxidation, original oxidation number of the iodine in the oxide must be from a 0, again. Now the oxidation number of the iodine in this oxide therefore must be a plus 5 to a 0, so that there is 5 electron unit change per iodine, and because there are 2, it is a total of 10 electrons. Okay, so therefore the answer is B. Alright, now I hope you liked the video, and I hope you have learned something from the video. If you'd like to join us, please don't forget to contact us, or just click the link to sign up for our classes. Okay, I'll see you soon. Bye.